this video, we are going to learn about the EM radiation, circular dichorism, surface plasma resonance, magnetic plasma resonance. These topics are not that much connected, but we will be dealing with them together for our convenience only. And first, we are going to learn about the electromagnetic radiation. What is electromagnetic radiation? Are the properties of electromagnetic radiation and all those related information. So, electromagnetic radiation is a form of energy transmitted through space with enormous velocity. It has both wave and particle properties. In other words, it has an alternative field of electrical and magnetic force, thus possessing an electrical component and a magnetic component, along with wave and particle properties. These two are mutually perpendicular to each other and to the direction of propagation as mentioned. The best example of electromagnetic radiation is light. So when we just draw a picture of this electromagnetic wave, we will be drawing an x-axis and y-axis, and we will be extending the y-axis into the downside of x-axis, and then we will be drawing a wave with a crest and trough, and wavelength is represented by drawing, and the amplitude can be seen. Electric component will be there in this wave. Direction of propagation can be represented into the right side, and magnetic component will be there, and the wavelength can be represented. So electromagnetic radiation moving along an axis is represented. So wave properties of electromagnetic radiation, we will be learning about that. The distance between two successive maxima of an electromagnetic wave is called wavelength. That is the difference of wavelength. Difference between two crusts, I guess. So, if a radiation beam has only one discrete wavelength, then it is monochromatic beam. And if it has several wavelengths, then it is heterochromatic or polychromatic beam. The total number of wavelengths units which pass through a given point at unit time is called frequency. The wave number represents the number of waves per centimeter in vacuum. So now we have learnt about many terms, but I will be explaining each of these terms once again. First, we have learned about wavelength. The distance between two successive maxima of an electromagnetic wave is called wavelength. If a radiation beam has only one discrete wavelength, then it is called monochromatic beam with same wavelength, only one type of wavelength, that is the monochromatic beam. And if it has several wavelengths, then it is called heterochromatic or polychromatic beam. So whether a wave is monochromatic or polychromatic, it is solely depend upon the wavelength. Okay. The total number of wavelengths units which pass through a given point of unit time is called frequency. The wave number represents the number of waves per centimeter in vacuum. The velocity of an electromagnetic radiation is the product of the wavelength and frequency, like V is equal to F lambda. We have learned this earlier. V is equal to F lambda, where F is equal to frequency and wavelength is equal to lambda. And V is nothing else but the velocity. Wavelength lambda, frequency F, number of lambdas that passes through a given point at unit time. Wave number, number of waves per centimeter in vacuum. Velocity depends on medium through which it propagates. If it has only one type of wavelength, that's monochromatic. The velocity also depends on the medium through which the electromagnetic radiation passes. The relationship between frequency, wave number and velocity can be shown by the formula V is equal to Cf V is equal to Cf, where C is the velocity of light through vacuum. And particle properties. Electromagnetic radiation exhibits refraction and reflection and possess a stream of as a stream of discrete particles of energy called photons or quanta. Photons travel in the direction or propagation of radiation. The energy of a photon is proportional to the frequency of radiation. Energy is proportional to frequency. Energy is proportional to frequency. Now, we are going to learn about the electromagnetic spectrum. The entire range over which an electromagnetic radiation exists is known as electromagnetic spectrum, which includes a wide range of wavelengths. Energy changes are induced in matter. Along with that, the radiation is represented in terms of its wavelength, frequency, or the wave number. The wavelength is expressed in nanometer or angstrom. And the term mu, like millimicron, is equivalent to nanometer. The gamma rays are the shortest waves emitted by the atomic nuclei. The X-rays are emitted or absorbed by the movement of electrons. The ultraviolet region of the spectrum forms the beginning for chemical analysis. In the visible region of the spectrum, the human eye can identify and correlate the wavelengths. The infrared region of the electromagnetic spectrum is associated with the changes in the vibration of molecules. The microwave region corresponds to the changes due to the rotation of molecules. The radio frequency region involves the energy changes due to reversal of rotation of nucleus or electron. Microwave region corresponds to the changes due to the rotation of molecules, and the radio frequency region involves the energy change due to the reversal of rotation of nucleus or electron. Sun, violet, indigo, blue, green, yellow, orange, red regions are there. IR rays, microwaves, radio waves, UV rays, X-rays, gamma rays will be there. Nuclear quotient is called gamma rays. X-rays, inner shell electrons are associated with that. UV rays, ionization of atoms, molecules and valence electrons. In case of visible, valence electrons will be there. And IR rays, molecular vibrations are associated with that. Microwaves, electron spin is related with it, and my radio waves are there. So nuclear spin will be associated with that. Now we are going to learn about the surface Plasmon resonance. This is a difficult topic, so we will be learning this very slowly. So what is surface Plasmon resonance? Surface Plasmon resonance, or SPR, is the resonant oscillation of conduction electrons at the interface between magnetic and positively permittivity material stimulated by incident light. Surface Plasmon resonance is a resonant oscillation of conduction electrons at the interface between negative and positive permittivity material stimulated by incident light. SPR is the basis of many standards for measuring adsorption of material onto planar metal, typically gold or silver surface, or into the surface of metal nanoparticles. It is the fundamental principle behind many color-based biosensor applications and different lab-on-a-chip sensors. Color-based biosensor applications. It is used in the color-based biosensor applications and different lab-on-a-chip sensors. So let's have an explanation about this topic. The surface plasmon polarization is a non-radiative electromagnetic surface wave that propagates in a direction parallel to the negative permittivity or dielectric material interface. Since the wave is on the boundary of the conductor and the external medium like air, water, or vacuum, or for example, these oscillations are very sensitive to any change of this boundary, such as the adsorption of molecules to the conducting surface. To describe the existence and properties of surface plasmon polarizations, one can choose from various methods like quantum theory, etc. The smallest way to approach the problem is to treat each material as a homogeneous continuum described by frequently independent relative permittivity between the external medium and the surface. This quantity, hereafter referred to as the material dielectric function, is the complex permittivity. In order for the terms that describe the electron surface plasmon to exist, the real part of the dielectric constant of the conductor must be negative and its magnitude must be greater than that of the electric. This condition is met in the infrared visible wavelength region of the air or metal and water or metal interfaces, where the real dielectric constant of a metal is negative and that of the air or water is positive. LSPRs, like localized SPRs, are collective electron charge oscillators in metallic nanoparticles that are excited by light. They exhibit enhanced near field amplitude at the resonance wavelength. This field is highly localized at the nanoparticles and decays rapidly away from the nanoparticle or dielectric interface into the dielectric background. Through far field scattering by the particle is also enhanced by the resonance. Light intensity enhancement is a very important aspect of LSPRS, and localization means that LSPR has very high spatial resolution or sub-wavelength, switched only by the size of nanoparticle. Because of the enhanced field amplitude, effects that depend on the amplitude such as magneto-optical effect are also enhanced by LSPRs. Well, let's learn about the implementation. There will be auto configuration and Kretschmann configuration. In order to explain and excite surface plasmons in a resonant manner, one can use electron bombardment or incident light beam. Visible and infrared are typical. The incoming beam has to match its momentum to match that of the plasmon. In the case of P polarized light, polarization occurs parallel to the plane of incidence. This is possible by passing the light through a block of glass to increase the wave number and the momentum and achieve the resonance at a given wavelength and angle. As polarized light polarization occurs perpendicular to the plane of the incident, cannot excite electron surface plasmons. Electronic and magnetic surface plasmons obey the following dispersion relation, where typical metals that support surface plasmons are silver and gold, but metals such as copper, titanium, or chromium have also been used. In order to excite surface plasmons in a resonant manner, one can use electron bombardment or incident light beam. Typical metals that support surface plasmons are silver and gold, but metals such as copper, titanium, or chromium have also been used. When using light to excite SP waves, there are two configurations which are well known. In the O2 setup, the light illuminates the wall of a glass block, typically a prism, and is totally internally reflected. The thin metal film, for example gold, is positioned close enough to the prism wall so that an evanescent wave can interact with the plasma waves on the surface and hence excite the plasmons. In the Kurtzman configuration. The metal film is evaporated onto the glass block. The light again illuminates the glass block and an evanescent wave penetrates to the metal ion. The plasmons are excited at the outer side of the film. This configuration is used in most practical applications. So, SPR emission, when the surface plasmon wave interacts with a local particle or integrity such as a rough surface, part of the energy can be re-emitted as light. This emitted light can be detected behind the metal film from various detections. Surface plasmon have been used to enhance the surface sensitivity of several spectroscopic measurements used, including fluorescence, Raman scattering, and second harmonic generation. However, in their simplest form, SPR reflectivity measurements can be used to detect molecular adsorption such as polymers, DNA or proteins, etc. Technically, it is common to measure the minimum angle of reflection, maximum angle of maximum angle of absorption. This angle changes in the order of 0.1 degree during thin about nm thickness film adsorption. In other cases, the changes in the adsorption wavelength is followed. The mechanism of detection is based on that the absorbing material causes changes in the local index of the refraction, challenging the resonance conditions of the surface plasmon waves. The same principle is exploited in the recently developed competitive platform based on lossless dielectric multi-layers supporting surface electromagnetic waves with sharper resonances. If the surface is patterned with different biopolymers using adequate optics and imaging sensors camera, the technique can be extended to surface plasmon resonance imaging. This method provides a high contrast of the images based on adsorbed amount of molecules, somewhat similar to Brewster angle microscopy. This later is most commonly used together with the Langmuir blow blowed jet rough. 4 nanoparticles. Localized surface plasmon oscillations can give rise to the intense colors of suspensions or soles containing the nanoparticles. Nanoparticles or nanowires of noble metals exhibit strong adsorption bands in the ultraviolet visible light regime that are not present in the bulk metal. This extraordinary absorption increase has been exploited to increase light absorption in photovoltaic cells by deposing metal nanoparticles on the cell surface. The energy color of this adsorption differs when the light is polarized along or perpendicular to nanowire. Shifts in this resonance due to changes in the local index of reaction upon adsorption to the nanoparticles can also be used to detect biopolymers such as DNA or proteins. Related complementary techniques include plasmon waveguide resonance, QCM, extraordinary optical transmission, and dual polarization interferometry. SPR immunoassay. The first SPR immunoassay was proposed in 1983 by Lundstrom, then of the Institute of Technology of Sweden. They adsorbed human immunoglobulin onto a 600 angstrom silver film and used the assay to detect anti-human IgG in water solution. And like many other immunoassays such as ELISA, an SPR immunoassay is label free in that a label molecule is not required for detection of the analyte. Additionally, the measurements on SPR can be followed real time, allowing the monitoring of individual steps in sequential binding events, particularly useful in the assessment of, for instance, sandwich complexes. Material characterization. Multipara metric surface plasmon resonance, a special configuration of SPR can be used to categorize layers and stacks of layers. Beside binding kinetics, MPSPR can also provide information on structural changes in terms of layer true thickness and refractive index. MPSPRs have been applied successfully in measurements of lipid targeting and capture. CVD deposited a single monolayer of graphene as well as in chromator thick polymers. Data interpretation. The most common data interpretation is based on the Fresnel formulas, which treat the formed thin films as infinite continuous dielectric layers. This interpretation may result in a multiple possible refractive index and thickness values. However, usually only one solution is within the reasonable data range. In multi-parametric surface plasmon resonance, two SPR curves are acquired by scanning a range of angles at two different wavelengths, which results in a unique solution of both thickness and refractive index. Metal particle plasmons are usually modeled using the Mice-Scarletic theory. In many cases, no detailed models are applied, but the sensors are calibrated for the specific application and used with interpolation within the calibration curve. Examples: layer by layer self-assembly. SPR curves measured during the adsorption of the polyelectrolyte and then a clay mineral self-assembled film onto a thin gold sensor. One of the first common applications of surface plasmon resonance spectroscopy was the measurement of the thickness and refractive index of absorbed self-assembled nanofilms on gold substrates. The resonance curves shift to higher angles as the thickness of the absorbed film increases. This example is a static SPR measurement. When higher speed observation is desired, one can select an angle right below the resonance point, the angle of minimum reflectance, and measure the reflectivity changes at that point. This is the so-called dynamic SPR measurement. The interpretation of the data assumes that the structure of the film does not change significantly during the measurement. Binding constant determination, association and dissociation signal will be there, the example of output. And the affinity of two ligands has to be determined. The binding constant must be determined. This is the equilibrium value for the product quotient. This value can also be found using the dynamic SPR parameters, and as in any chemical reaction, it is the association rate divided by the dissociation rate. For this, a bait ligand is immobilized on the dextran surface of the SPR crystal. Through a microflow system, a solution with the preanalyte is injected over the bait layer. As the preanalyte binds the bait ligand, an increase in SPR signal expressed in response units is observed. After decided association time, a solution without the preanalyte, usually the buffer, is injected on the microfluidics that dissociates the bound complex between bait ligand and preanalyte. Now, as the preanalyte dissociates from the bait ligand, the decrease in SPR signal expressed in resonance units is observed. From this dissociation rates, the equilibrium dissociation constant can be calculated. The actual SPR signal can be explained by the electromagnetic coupling of the incident light with the surface plasmon of the gold layer. This plasmon can be influenced by the layer just a few nanometer across the gold solution interface. The beta protein and possibly the prey protein binding makes the reflection angle change. Thermodynamic analysis. As SPR biosensors facilitate measurements at different temperatures. As SPR biosensors facilitate measurements at different temperatures, thermodynamic analysis can be performed to obtain a better understanding of the studied interaction. By performing measurements at different temperatures, typically between 4 and 40 degrees Celsius, it is possible to relate association and dissociation rate constants with activation energy and thereby obtain thermodynamic parameters including binding enthalpy, binding entropy, Gibbs free energy, and heat capacity. Next is the pairwise epitope mapping. As SPR allows real-time monitoring, individual steps in sequential binding events can be thoroughly assessed when investigating the suitability between antibodies in a sandwich configuration. Additionally, it allows the mapping of epitopes, as antibodies of overlapping epitopes will be associated with an attenuated signal compared to those comparable of interacting simultaneously. Next is the magnetic plasmon resonance. Recently, there has been an interest in magnetic surface plasmons. This require materials with large negative magnetic permeability, a property that has only recently been made available with the construction of metamaterials. So SPR, surface plasmon resonance, is a resonance oscillation of conduction electrons at the interface between negative and positive permanently materials stimulated by nuclear light. It is used in many standard tools for measuring adsorption of material and on the metal surface or onto the surface of metal nanoparticles. It is the fundamental principle behind many color-based biosensor applications and lab on a chip sensors and related things.